Bismillahirrahmanirrahim. Assalamu alaikum everyone. So today we will be having 21st lecture, right? And we will be talking about sequential circuits. So let's start. So before starting, let's talk about combinational versus sequential circuits, right? So in a combinational circuits, we have the input and the output, right? And at any point in time, output depends only on the input, right? And whenever we change the input, obviously we will get a change in the output, right? So we don't have any memory, right? You can say it don't keep any sort of history, right? And finally the time sequence is ignored, right? So that's a bit about combinational circuits. On the other hand, in a sequential circuit, we have the input and we have the output, and you can see a feedback, right? But the feedback is connected to the input via the memory, right? So you have a feedback, right? And you need memory in order to store the previous state, right? So the stored information at any time defines a state, right? So we need to store the state, and for that we need memory, right? And more importantly, the output is a function of the input, right? And the previous state, right? You can say the output is a function of input, right, present state, and maybe the previous state, right? Or you can say the previous input, right? So this is something about sequential circuits, right? So these are the examples we can have regarding sequential circuits. You can see that in a traffic light signal, we need to store the current state. We have to take care what was the light before, because we have a sequence, right? Whenever we think about the light signal, you can see we have a sequence, particular sequence, right? You can say that if we have the red, then there will be a yellow and green, right? And there is a gap, predefined amount of gap in between, right? So this is the, so we need memory, right? And we have to take care what was the previous state, right? Or what was the previous input. So that is an example of a sequential circuit, right? Similarly in ATM, right? You can see we follow a certain number of steps in sequence, right? And timing is important, and the previous state is remembered, right? So we need memory. Similarly, the vending machine for a coffee, for cold drink, and so on and so forth, right? So these are the examples of sequential systems, right? And then let's talk about the adder, right? And we have a adder here, right? You can see that 4 full adders are cascaded, right? And what we want or wish, we want to add 2 4-bit binary numbers, right? So you can see the carry is propagating, right? So this is the carry in, and this is carry out, right? And this is carry in for the next adder, right? Similarly, this is carry out, and this is the carry in. So you can see the ripple effect of the carry, or you can say the carry out propagation, right? So at a time, one adder has to be active, right? Because we need to, right, apply the carry out as an input for the next adder, right? So here we will activate this one, right? So we will get, if we start here, right, then we have to activate this first, right? So we will be adding the corresponding bits. Those are A0 and B0, right? And then this is the carry out, and this will be the carry in for the next here we will be adding A1 and B1, right? These are the corresponding bits at the first slot, right? And then this is the carry out here, and this will be the carry in for the third full adder. And here we will be adding the corresponding bits in the third slot, right? So because we have started from 0, so this is A2, B2, right? And here again we have the carry out and carry in for the next adder, right? So here we have the sum, right? And this is the carry out, right? So we need 4 adders, right? And only one adder has to be activated at a time, right? So this is the combination circuits, right? Circuit, and you can see the difference, right? Here we don't have any memory, right? And we don't have any control signal, right? Right. So this is the sequential order adder, right? And here you can see we have used only one full adder, right? So this is the sum, right? And these are the numbers, 4-bit first number and the 4-bit second number, right? So here you can see that this is the carry out, and here we have 1-bit memory, and this is the carry in for the next slot, right? So 1-bit memory and 2 4-bit memory in order to store the binary 4-bit binary numbers so that we can add them, right? So here we need 4 clock signals, right? So on the first clock, what will happen? This A0 and B0 will be added. We will have the sum, right? And then this is the C out, carry out, and this carry out will be stored here, right? So that we can use it for the next addition, right? So next we have a shift right process, right? So that shift right process will shift this bit here, right? And then those corresponding bits will be added alongside C in, right? And we have a sum. Again we have a carry out, right? And then this carry out will be stored, and this will be used for the next addition in this slot, right? And so on and so forth, and we will be getting. So you can see the difference, right? So we have a memory here, and we need a control signal so that we can proceed or move the bits to the right, and then we can perform the addition, right? So this is the sequential adder, right? And that was the combinational adder, right? So but there is some problem with the latches, which we studied in lecture before, right? So the problem is that, for example, if we have clock is equal to 1, right? So the question is, what will happen if Q, what will happen to the value of Q when clock goes to 0, right? So it means it goes from high to low. So the problem is that, as we have discussed, that the latch transparently moves data as long as the clock remains active, right? So so there will be change till we have this level, right? That is 1, right? Or high, you can say. So you can say that there will be uncertainty, right? So the value will be changing, right, or oscillating as long as we have the active clock level, right? So in order to avoid this uncertainty, right, we have to do something else, right? So it means we cannot rely totally on latches in order to have storage elements, right? Okay, so that's we got up till now, right? If we compare today's lecture, we talk about today's lecture, right? And we think about the lecture that we have a day before, right? Then you should think about the difference between latches, right, and the flip-flops, right? So latch, you can say, is the level sensitive, right? And flip-flop, on the other hand, they are edge sensitive, right? So they will store data on the rising or the falling edge, right? So we can have different type of flip-flops and their functionality is different, right? So as we know that if we have a Boolean function, we can define the truth table, right? And similarly we can have the circuitry. So but for flip-flops we can have the characteristic functions, and we can also have the characteristic equations for the flip-flops, right? Okay, so this is the same, the difference between fundamental sequential components, right, that are flip-flop and latches, right? So as we have mentioned that latch is level sensitive while the flip-flop is edge sensitive, right? And both can store 1-bit data, right? And they need a control signal or a clock, right? So this again latches, right? So is a temporary storage device, right? And it has 2 stable states, and that's why we can call it a bistable, right? So latch is somewhat different from the flip-flop, right? And for regarding difference, we already know the difference lies in the methodology of changing their state, right? The output of latch depends on its current inputs, right, and on the previous output, right? Right. So as I have mentioned that we need a control signal, right, in order to control or manipulate the functionality of the sequential components, and these are latches and flip-flops, right? So that control signal, we normally call it a clock, right? So it we generate a clock signal from an oscillator, right? So we have a circuitry, right, and that circuitry produces an alternate signal, right, that oscillates between 0 and 1, right? And this will continue, or this will happen as long as we have the circuitry switched on, right? So we normally use this to synchronize the flow of data, right, in digital systems. So you can see this is the diagram timing. You can say this is the representation of a clock, right? So here you can see that we have the rising edge, that is called positive edge, right? And here we have the falling edge, and we can name it a negative edge, right? So this is the level, if we talk about the level, or because we have already discussed about the level, because latches are level sensitive. So this is the positive level, right, and this is the negative level. So that's what we were talking about, that the latches will remain, right, or latches will continue changing its state, right, during this positive level, right? So there will be transients during that level, right? So it depends on the length of this level, right? On the other hand, the flip-flop, they are edge sensitive, right? So maybe if we have a flip-flop that is positive edge sensitive, or then we can have another type of flip-flop that is falling edge or negative edge sensitive, right? So this is something about the clock, right? So here we have the D-latch, right? So you can see that how we proceed. We have used the same SR latch, right? So here you can see we have the SR latch, right, with the control signal, that is the clock, right? But the problem with this SR latch is that we have a race condition, right? Or we have a discontinuity at 1 1. Whenever we have 1 1, right, both Q and Q bar are the same, but logically speaking they should be complement of each other, right? If Q is 1, Q bar should be 0. If Q is 0, Q bar should be 1, right? So this is the violation of our digital logic axioms, right? So what we did over here, in order to avoid this, right, race condition, what I did over here, I have applied a signal that is called D input, right, into this S, right, and then I have complemented this input and applied this at R, right? So you can see that if I paired them all, right, 0 0 1 1, because then we cannot have this state that 0 0, right, and 1 1, because this is complemented, right? So we will have 0 1 because one input, so there are only two possibilities, right? So D, this is the clock, right, or control signal, and this is Q and Q bar, right? So here you can see we have 0 on when clock is 1, right? So Q is following D, right? So here again D1, this is the control signal, this is high, right? So Q follows D, and here whenever we have the control signal 0, irrespective of the value of D, it will retain the previous state, right? So in other words, you can say that D passes to Q, right, whenever we have the high or active clock, right? So this is the D latch. Okay, then here we have the transparent latch, right? So the difference over here, we have the enable, right? So you can see that whenever enable is 0, right, so we will have the previous state, that is whatever the previous state was, that will be retained, right? When enable is high, right, so Q follows D. Enable high, Q follows D. So on enable high, right, the input is transferred to the output, right, or a gate is open and input is received at the output, right? So this is the transparent latch. So here we have the timing diagram for the transparent latch, D latch, right? So here you can see we have 3 signals, right? This is Q, and this is D, and this is enable, right? So from this timing diagram, you should be able to understand the latch, right? So here you can see that we have enable low, right? So this is Q, this is D, right, and this is Q, right? So here we have the latch, Q is equal to 0, and that will remain the same, right? So here you can see enable is high, right, and we know for a D latch Q follows D, right? So you can see the same replication till here, right? So here you can see that we have right, so there is a change in D, right, that is the input, but as we have enable low, right, so the Q will be latched, right? So Q is equal to 1, that will be latched till the next enable, right? So here enable again high, right, and you can see the ditto copy, right, or the replication of the same D, right? So you can see we have the same D over here, right? So here again we have enable low, right? So again Q will be latched, right? And here again we can see the transparent switching, right? Or the data is moved transparently from input to the output, right? So you can see the transparency, right? So you can have the same sort of replication or copy of the signal whenever we have enable high, right? So here you can see the latch functionality, transparent latch functionality with the timing diagram, right? So and this is the integrated circuit IC, right? 74LS75 for D latch, and we have the function table, and you can see we have inputs, outputs, right? So this is D, enable, Q, and Q bar, right? So we have here low, high, right? And this is don't care, and this is the complement, right? Q bar. So you can see that we have whenever enable is high, right? So Q follows D, enable high, Q follows D, right? Whenever enable is low, we have the previous state, right? So these are the pin configurations, right? So you can see that we have different pins, and they have their tags, names, starting from 1 till 16, right? So you can see that we have 4 D latches, right, inside this IC, right? 1, 2, 3, 4 latches, right? You can see D1, D2, D3, D4, right? And these are the outputs, right? Q1, right? Q2, and Q3 and Q4, right? And these are the complements, right? So we have Q1 bar, right? And here we have the Q2 bar, right? And here we have the Q3 bar and Q4 bar, right? And this is the enable, right? Here we have another enable, right? So this is the enable for latch 1 and 2, and this is the enable for latch 3 and 4, right? So whenever this will be high, right, so those latches will be activated, right? And here whenever we have this high, we have 3 and 4 activated, right? So this is the IC for D latch, right? And then we can use multiplexers in order to design a D latch, right? So let's talk about multiplexer. So this is a 2-into-1 multiplexer. We have 2 inputs, 1 control signal and 1 output, right? So as we have 1 control input, so we can have only 2 values, right? When A is 0, so that means I0 will be selected. When A is 1, so I1 will be selected, right? So A0, right? So this I0, right, will be selected. So you can see that the switch is connected here, right, when A is equal to 0, right? And then when A is equal to 1, then we have the connection here, right? So you can see the Boolean function, right, or equation for this, right? So Z is equal to A bar dot I0 plus A dot I1, right? Right. So it means you can say whenever we have A is equal to 0, I0 will be passing to the output, right? Because A0 is equal to 0, A is equal to 0, so A0 1, right? So we will be having the I0, whatever the I0, if it is 0, if we have the 0, if it is 1, we will have the 1, right? So this is the functionality. These are the data inputs, right? So that's what we were talking about, right? So we have a D latch, right? And but we have used multiplexers, right? So you can see we have a multiplexer with 2 inputs, right? So this is the control signal or the control input, right? Or we have clock, right? And this is the output. So you can see that this is the positive level triggered D latch, right? So it means we must have 1 at clock, right? So 1 at clock mean that 1 will be selected. So on the active clock edge or clock, on the active clock, right, we will be on the active level of clock, because we are talking about latches, right? They are level sensitive. So on the active level of clock, this switch will be connected here and D will be transferred to the Q, right? Or Q will be following D, right? So you can see the table over here, right? So whenever clock is 0, right? So no change, right? So we will be having the previous state, right? And then when clock is 1, right? So 1 is selected and Q follows D, right? So Q follows D. Here clock is 1, right? So it means 1 has to be selected and Q follows D, right? So you can say D passes to Q when C is equal to 1 or clock is 1, right? So this is the negative level triggering, right? And you can see here, as opposed to the scenario over here where we have applied the feedback to 0, so here we have applied the feedback to 1 because we have the negative level triggering over here, right? So whenever we have clock 0, so it means we have this switch connected over here, right? So it means on 0 Q will follow this D, right? So we can have the table, right? D when clock is 1, right? Then no change, we will have the previous state. And whenever clock 0, Q follows D, clock 0, Q follows D, right? So this is the D latch, but we have used multiplexer, which we already know and constructed by using the conventional combinational logic and or not, right? So let's talk about the flip-flop, right? The problem with latches is they are not good for synchronous logic, right? And what we can do, we can have cascading of two flip-flop or two latches in order to build the flip-flop, and we will see in a couple of moments, right? Moreover, the possibility of two cascading combination circuits feeding each other, right? This is what we discussed regarding latches, right? But the problem is they generate oscillations, right? And as a result of those oscillations, we have transients, right? And we don't have control over those transients, right? So but in order to resolve this problem, we can have a special timing control signal, that is a clock, right? So rather than the level sensitivity, we will be focusing or talking about the edge sensitivity, right? So the clock then can be used to restrict the time, right, in order to prevent the transients and unstable behavior, right? So there is a relationship between latches and flip-flop, right? Because you can see that here we have cascaded two latches, right? So these are two D latches, right? And if I place a box, right, here, right? So this is what? This is a flip-flop, right? Right? So you can see that we have cascaded two latches, right? So you will see that as a result of this cascading, we will overcome, or we are able to resolve that sort of problem. The generation of oscillations, right, and transients, right, and we are able to control by cascading two latches. So it means that there is a relationship between the latches, right? So you can say that the latches are the basic building block for flip-flops, right? Okay, so that's what we were talking about, master-slave delatches, right? So here this is the same diagram, but here we have master and slave, right? As the name is indicating that slave will be following master, right? So here we have two latches and they're cascading, and only one latch will be activated at a time because we have a clock here. The same clock is complemented and applied to the slave, right? So output changes on falling edge of the clock, right? So you can see that we have this. If we have activation here for the rising edge, so that will be maybe that is the inversion, right? So this is the function table for D flip-flop, right? Here we have the edge triggering, right? So you will see the difference. We have edges, right? So this is the rising edge, right? So you can see that this is clock D, Q and Q bar. So Q follows D on the rising edge of the clock, right? Whenever we have a clock 0, right, there will be no change, right? So rising edge, right, Q follows D, rising edge, Q follows D, right? D gets last to Q, right, on the rising edge of the clock, right? So this is the timing diagram. So we'll see that we have the clock. So this is the rising edge, right? So this you can say from low to high, right? So you can see that Q follows D, right? So Q is low, right? So it is following D because D is high, right? And it will remain high till the next rising edge, right? And here Q follows D. So D is low, so Q has to be low, lowered down, right? So it will remain low till the next clock, right? And here this is the next active edge, right? Not the level, because we are talking about the flip-flops, right? So here you can see that we have the Q follows D, right? So you can say because this is 0 and this will remain 0, so there is no change, right? And here you will see that Q follows D, right? Because we have the active edge, right? So D is high and Q has to be high, so it will remain, right? Because D is high, so it will remain high till here, right? So here no change, right? So this is the timing diagram for a D flip-flop. So the difference is that here we have the change, right, only at the active edge, right? So you will see the difference, right? So here you can see, we can see the replication, right? So here we have the replication, right? So but over here you can see that don't have the replication, right? So there is no replication, only we have some transition at the edge, right? So these are the edges, right? If we talk about the clock edges, so these are the positive edges, right? Positive edge, and these are the negative edges, right? So this is, if this is 1 and this is 0, and you can see that we have negative and positive edges, right? So here we have the function table for positive edge triggered and negative edge triggered D flip-flops, right? So you can see that we have D flip-flop. This is the block diagram or symbolic representation for D flip-flop. Here we have D, this is clock, right, arrow, this is Q and Q bar. Here again we have D and we have the clock, but there is a bubble, right? So this is the negative edge triggered clock, right? So you can see the arrows. We have an arrow up, right? So here we have an arrow down. So Q follows D on the active clock edge, right? So this is the falling edge and this is the rising edge, right? Right. So these are the clocking events, right? If I have to consider the clock as an event, so you can see that here we have a transition from high to low, right? Or we normally call it a falling edge, right? But there is a transition. So here we have from low to high. This is the rising edge, right? And here you can see that we have positive edge triggered flip-flop, which we already discussed, right? But the difference over here is that here we want to show the edge, right? How the transition occurs, right? So high to low, right? And low to high. Okay, so again clocked D flip-flop, right? So you can see the timing diagram, right? Again here we have clock, right? So you can see the oscillations, right? And this will continue, right, forever, right? And this is the input, right, D. So it is normally better if we place those lines, right, dashed lines, right, regarding the active clock edge, so that we can draw the Q, right? So here you can see we have Q, right? So Q is 1 when we started, because you can say that 1 is already stored there, right? And on the because this is the rising edge, right? So D clock and Q bar, right? So Q is 1 when we have started, right? And then on the active or rising edge, Q has to follow D, right? So D is low, so it will go low, right? And it will remain low till the next rising edge, right? So you can see Q remained low till the next rising edge. So here D is high, right? And we moved here, right? And here again we have to look at D, right? So D is low, right? So there will be a toggle, right, or transition from high to low, right? Because Q has to follow D, and then Q will remain in the low state till the next active edge or rising edge, right? So here D high, so Q will be high, right? And it will remain high till the next active or rising edge, right? So here we have D high, right? And again Q follows D, it will remain high till the next rising edge, right? So here we have D low, so Q has to be low, right? Again D low, so Q will remain low, right? So this is the timing diagram for a clocked D flip-flop, right? And this is the same that we have added something new, that so here you can see that this is the key difference, right? So enable and clock input, right? So flip-flop clock input is edge sensitive, as we have already seen over here. Regarding flip-flop, it is edge sensitive, right, rather than the level sensitivity of a latch, right? The latch enable input is level sensitive, right? So this is the integrated circuitry, right, IC for D flip-flop, right? So here you can see that we have 74 LS 74, right? And we have input and the output, right? So but the difference over here is that's what we have not discussed so far, that is preset, clear, clock, and D, right? Q bar, right? So the only difference over here that we have preset, right, and clear, which we have not discussed so far, right? But rest of the entities are the same: clock, D, Q bar, right? So these are the inputs and these are the outputs, right? But here we have only two D flip-flops, right? So we have D1, right, and you can see D2 right here, and we have Q1, right, Q1 bar, right? So this is Q2 and Q2 bar, right? So this is the VCC for turning this circuitry on, right? And there should be a ground, so this is ground, right? And we have 4 control signals, right? So rather than 6 control signals, you can say that 2 clocks, right? So this is clock 1, clock 2, then we have preset 1 and preset 2, right? And here we have clear 1, right, and clear 2, right? So this is the integrated circuitry for D flip-flop, right? So it provides 2 D flip-flops, right, but with more control as we have preset and clear, right? So if we talk about RS latch, right, so there are certain problems, right? One problem is that we have the race conditions, right? If we talk about the RS latch, that can be built from NOR gate and NAND gate as well, right? So we have 2 race conditions, right, that are 0 0 and 1 1, right? So we want to use those different conditions in an effective way because they are undefined, right, regarding the RS latch, right? And the second problem is that we don't have toggle state, right? So the transition state. So we want to achieve that transition state in order to use it in an effective and efficient way, right? So in order to resolve those problems, let me introduce the JK flip-flop, right? So you can see that we have no race condition whenever we have 0 0 and 1 1. Moreover, whenever we have 1 1, you will see that the output is toggled, right? So this is somewhat different from the sequential components we have discussed so far, because we don't have such scenario where we have 2 inputs same and the previous state is complemented. If we have a 0 here, we will be having 1. If we have a 1 here, we will be having a 0. So it means a toggle, right? So we have resolved the race conditions in addition to the one more feature which we can utilize in order to construct more effective and efficient sequential circuits, right? Right. So this is JK flip-flop. You can see we have the table. So here you can see Q follows J on the active clock, right? And these 2 are the exceptions, right? So here 0 0 no change, right, and 1 1 toggle, and for the rest of the 2 combinations, Q follows J, right? So this is the rising edge, so you can see Q follows J, Q follows J, and this is no change, right? No change. And here we have the complement of this clock, or you can say that we have an arrow that is pointing down, right? Right. So this is the same stuff, right? So here we have the same table, right? You can name this as an excitation table, right? So we have J, K, clock, Q, Q bar, right? So we can see that this is the clock, Q, no change, clear, right? So it means Q has been cleared, right? And this is Q has been set, because we have 1 at Q, and here we have a toggle state, right? So this is the rising edge of the clock. This is the timing diagram, right? So you can see that we have Q, right? That is the output, J and K, 2 inputs, and this is the clock, right? So as we are talking about flip-flop, so you will see the change at the active edge. So this is the clock. So as this is the timing diagram for a rising edge, right? So here you can see clock, right? So Q is low when we started, right? So here we have 0, 1, right? So this is the active edge, right? So it means Q follows J, or you can say this set, because we have put Q, we have made Q is equal to 1. So this is setting the flip-flop, right? And here this is the different scenario. We have 1, 1, right? But before we have a race condition regarding the SR latch, right? So here we have something new, right? And JK11, right? And you can see that we have Q1. So here we have a toggle, right? From 1 to 0. So you can see this is a trigger or toggle from low to high to low, right? And this will remain low till the next clock, right? So again here we have the active edge J1, K1, so again toggle, so from 0 to 1, right? So you can understand the toggle, right? If we have a 0, we will have 1, right? And here we have a 1, we have 0, we move to 0, right? So this will remain in this state till the next clock, right? And here we have the next active edge, right? So here we have 1, right? And J. So here Q follows J, right? So we have cleared, right? Or reset the latch flip-flop, right? So here again, right? And here we have both 0, 0, so there should not be any change. So it will remain in this state, right? Previous state till the next clock, right? So here we have J1, K 0, right? So it means we have to set the flip-flop, right? Q1, right? And till the next active edge, right? So this is the timing diagram for JK flip-flop, right? So you can see the difference regarding the toggle, right? So how we can construct the JK flip-flop by using the D flip-flop, right? Because we already know the D flip-flop, right? So that's why we will try to construct the JK flip-flop by using D flip-flop, right? So if I construct the K map, right? So you can see we have JK, right? And Q here, right? So JK, and this is the same stuff we know very well, right? So we start 0, 0, 0, 1, 1, 1, 1, 0, right? So you can see that there is a jump here, right? From here to here we have 0, 1, 1, 0, 1, 1, right? So this is 0, 1, this is Q. So now we can have the placing of ones, corresponding ones, right? And if you look at the truth table of JK flip-flop, so we can fill this table, right? So 0, 0, right? And Q 0, right? 0, 1, right? So we have 0, 0, right? And then we have 1, 1, 1, 0, right? So you can see that we have pairs. This is first pair and this is the second pair after banding, right? So or rotation, giving the rotation. So this is what, right? So here k will be cancelled and we have j, and this is q bar, right? And this is what, this is after the banding we will left with k bar, right, and q, right? So we will have, so you can see that d is equal to j q bar, right? So j, and where is q bar? So this is the second input, right? So let me write down with the pen, right? So here we have j, right? So this is what, j, so I will write down this with mouse pointer, right? So here we have q bar, right? And here we have k bar, right, and q. So and then that will be odd here, and this is the d, right? So and this is here we have the j and k bar, so this is k bar, right? So if I place a box, right, and this is what, this is the JK flip-flop, right? But what we have used a D flip-flop, right? And in relation to the D flip-flop we have used the fundamental combinational components that are and R, right? So this is the implementation of JK flip-flop by using D flip-flop, right? So this is the same stuff, right? So here the same timing diagram for JK flip-flop, right? So so here you can see that we have the same stuff, right? But here we have clock, right? Because in the previous I think there is no clock, so here we have the clock, right? So you can see the same equation, right? And we have JK flip-flop, right? And the difference is here we have a clock, right? So it means we have a clock here, right? And this is the example, right? So another example in order to have more about JK flip-flop, right? So we have to determine the output Q, right? Reset, right? So it means reset mean we have a 0 at Q, right? So here you can see that we have we have J, K, right, and Q, right? And so as we have flip-flop in the 0 state, right? So this is the clock, right? And this is JK, J1, K1, right? So here you can see we will have a toggle, right? Because we have a previous state 0, so it has to toggle, right? And will attain 1, right? So it will remain 1 because here we have the falling edge, right? So this is the falling edge, or you can say falling edge, right? So arrow, right? So this is the falling edge, right? So here again you can see that we have J0, 0, no change, right? And again here we have J0, K1, so flip-flop has to reset, so right? So we will have 0, right, at the output, right? Again 1, 1, J1, K0, so flip-flop has to set, so we will have 1, again set. So this is the diagram for timing diagram for JK flip-flop, right? But we have the falling edge, right? So we have discussed JK flip-flop, right? And we have seen a new scenario where whenever we have J and K 1 1 and we achieve the toggle, right? If we have both J and K 1 1, right, we will toggle from 0 to 1, right? And if we have might have 1 here, then we will have a 0, right? But if we can attain or achieve the same toggle by having one input, right, so that will be more beneficial for us, right? That's what we want to achieve regarding the T flip-flop, right? So you will see that we will arrange or use D flip-flop, right, in such a way by using some fundamental logic gate, right, that we can achieve the same toggle by having one input only, right? So here you can see we have XOR gate, right, and this XOR gate is this output is feedback, right, and here we have a T and this is the D flip-flop, right? So if we look at the table, right, so here we have T 0, right, Q naught, right, bar, and whenever T is 1 we will have a toggle, right? So it means if we have a Q1 it will toggle to 0, if we have Q0 it will toggle to 1, right? So rather than using 2 input JK flip-flop, now we are having 1 input flip-flop in order to achieve the toggle, right? So this is somewhat different, right? So this is the T flip-flop implementation by JK flip-flop, right? So you can see we have the K map, right? So J is equal to T, K is equal to T, right? Right. So this is the same T flip-flop implementation, but by using JK. So regarding the JK flip-flop, we already have the function, right? Boolean function. So you can see if I put J is equal to K is equal to T, right? So because this is understandable, right? You can see we have T at both of the inputs J and K, right? So I can place mathematically I can place J is equal to K is equal to T. So I put this in this equation, so you will see that we will have T Q bar and T bar Q, and that is equal to T, this is what? This is XOR, right? Q. So you will have this XOR gate, right? So this is the feedback, right? Q, and this is D. So we will be having this, right? So T flip-flop, right? And then we have the implementation of JK flip-flop by T flip-flop, right? So here we have the use T flip-flop, right? So you can see the K map, right? So here we have two pairs, 1 1 and 1 1 here. So as a result of this pair, we have J Q bar plus K Q, right? So this is something different from the implementation of JK flip-flop by T flip-flop, right? So if I go back, right? So T flip-flop implementation by JK flip-flop, right? So here you can see that we don't have any inversion regarding K, right? Okay, right? So this is the equation, right? So you can see that we have J Q bar, J, this is Q bar, and this is K Q, right? And these are the flip-flops and their corresponding characteristic tables. We can also have the characteristic equations, right? So this is T, this is Q follows D, right? Q follows D when except these two, because here we have a toggle, here we have a no change, right? So we are having the same toggle but only having one input, right? So T0, right? So this is no change, and T1 we have a toggle here, right? And then let's talk about asynchronous design or asynchronous sort of inputs, right? So we cannot avoid asynchronous circuitry, right? So there are a lot of different user interfaces, a lot of different devices, right? Speed devices, right? And then we can have a lot of different circuitry that is functioning asynchronously, right? So but the problem is that it's difficult to design, right? And we don't have design tools for analysis, right? And that's why we prefer synchronous logic as opposed to asynchronous logic, right? Okay, so we have two sort of sequential circuits, synchronous, right, and asynchronous, right? So in synchronous, the behavior of the circuit is totally clocked, is totally controlled by the clock signal, right? So we can say that the behavior is clocked, right? But for asynchronous, right, the behavior depends on the input signals at any instant of time and the order of the change in the input, right? And the example of an asynchronous circuit is a combinational circuit with feedback, right? You can say SR latch, right? So here we have asynchronous inputs, not the circuitry, right? So here you can see that we have a preset and clear inputs, right, that are asynchronous because they function independently from the clock, right? So whenever, if you look at this table, right, characteristic table, so you will find whenever we have preset, right, so here preset 0, so irrespective of the clock and D, we will set the latch, right? Whenever we have preset 0, right, so irrespective of the clock, we will so this is unavoidable, right? So here we have preset 0, so here we have clear 0, so you can see that we are resetting the latch irrespective of the clocks, right? So that's why we call those inputs as asynchronous, because they function independently from the clock, right? So here we have the D flip-flop timing diagram, but the addition over here is preset and clear, right? So here you can see that D clock, right, and preset, because if you look here, we have active low, right? Preset active low due to this bubble, and clear is also active low due to this bubble, right? So here we have D flip-flop, right, but with preset and clear timings, right? So here you can see that D high, right, so clocked, right, so it means Q follows D. So here again preset high, clear high, right? So we are having the same normal operation of the D flip-flop, right? So it means Q follows D, because D is low, so it will be low, right? But here you can see that preset is low because we have an active low, right? So it means it has to be preset, right? So we have to make the flip-flop preset, right? So you can see we have make it preset, right? So it will remain, right? So here again on the next clock again we will so here we will not care about the clock, right? So preset, right, so this will remain here, right? And here we have preset 1, right, and clear, right? So it means clocked, right? So here both 1 1, because we have active low, so there is no impact of preset and clear, right? So here you can see another change, right? So when clear is low, so it means we have to clear the flip-flop. So here you can see from 1 we have 0, right? So Q is equal to 0, clear. So here we have preset, right? Because we have active low, right? So again, whenever we have preset and clear 1 1, so we will be relying on this clock, right? So then you can see that when they both are 1 1, right, so we will be following the edge, right? So this is the active edge, right? So Q follows D. So here you can see that Q D is equal to 1, so Q is also 1, right? So this is the D flip-flop. Again, asynchronous inputs, right? Over here we have JK, but with synchronous inputs, right? So we have clock, this is the bubble, and we have preset, but with the complement, and clear with also complement, right? So this is also asynchronous, right? And you can see the timing diagram, and here we have JK, right? And preset, active low, clear, active low, and you can see the timing diagram and you can solve it by yourself, right? And then here we have circuit, but with asynchronous inputs, right? So we have D flip-flop, right, with clock, with reset, right? But this is active low, and this is the function table. And we can also have the parallel data transfer regarding the D flip-flops, right? So here we have cascaded different D flip-flops, right? And we have the falling edge of the clock, right? And then we can also have the characteristic tables for all the flip-flops, right? So a characteristic table defines normally the operation of a flip-flop, right? But we have to represent that operation in a tabular form, right? So we can have the characteristic tables for all the flip-flops. These are the equations. As we can have equations for all the combinational circuits, we can also have the equations for flip-flop, right? So these are the characteristic equations for flip-flops, right? So that's all for today's lecture. So today we have discussed flip-flops, right? And we talked about different flip-flops, that includes JK flip-flop, D flip-flop, and T flip-flop, right? And we also discussed about asynchronous and synchronous inputs, and different sort of asynchronous and synchronous circuitry, right? So that's all for today's. मेरी तरफ से अल्लाह हाफिज़, अस्सलाम वालेकुम.